Hello, it's Keith here, and this is lesson 68 of the platform-specific series of my 650 assembly programming tutorials. This is actually a Super Nintendo tutorial, so it's arguably the 65816, but in these tutorials use the processor in 6502 mode, so that is relevant to today's example. Now, what we've done today is we've used interrupts to play some music. The music you heard there is being played with my ChibiTracks music player, but that's really academic. This is just an example on interrupts, really. So, how do interrupts work on the Super Nintendo? Well, there were a set of interrupt vectors, which is just a clever name for the address of the interrupt handler that you want to execute, that appear at the end of the footer of the ROM cartridge. Now, you can see the memory addresses that are used for this just here. So FFE0 onwards, all the way up to FFFF, there's 2 bytes for each. Now, there are actually 2 sets of these, and this is why it's important to know what mode the processors are in. So there's one set for the 6502 mode, and there's one set for the 65816 mode, and depending on what mode the processor is in when the interrupt occurs, is a different interrupt handler will be executed. Now, as I say, in our example today, the processor will be running always in 6502 mode, because that's how these tutorials actually run. I have a very small number of 65816 tutorials, but generally I use the SNES in 6502 mode because these are multi-platform tutorials and I'm porting code from other 6502 systems. Now, the VBlank interrupt is a NMI non-maskable interrupt, and that is what will be executed when the VBlank occurs, assuming they're enabled. So what we're going to do is we are going to set up our ROM cartridge, and that's what you heard playing the music earlier. So let's take a look at what we've got. So at the bottom of our cartridge, you can see we've got this footer block here. It starts at FFC0, and it's got the footer. I would call it a header usually, but it's at the end, so I guess it's a footer. And this is the sort of information about the cartridge itself. So we've got the program title here, we've got the checksum, and we've got various other things there. Those are all needed for the emulators, but what we're really interested in today is the vectors. So we have our reset vector here. This is the reset vector that starts our cartridge. There is a reset vector for the 65816 mode, but that is never actually used because it's when the processor resets, it always starts in 6502 mode, so it's impossible for a reset in 65816 to occur. So that doesn't exist, but what does exist is the NMI. Now, I've created this custom NMI handler, which is my interrupt handler for today. I've actually, just for example's sake, created one for the 65816 as well, but that doesn't actually do anything. You can see here it just goes to an RTI command. Now, a reason I put that in was really just to prove a point, and that is to prove that this is the one that is being executed when our music is playing. Okay, so first of all, let's take a look at how we actually get the interrupt handler to start. It's pretty straightforward. So all we need to do is we need to turn on the interrupt. Now, the interrupt is controlled by port 4200, and it's the top bit 7, that actually controls the NMI VBlank. So if we set that to 1, as we've done here, we get music. If I just change this to a 0, and if I run again, well, now we've got no music. We've also got no video, you'll notice, and that's because with the Super Nintendo, like a lot of other systems, you can't actually write to the video memory outside of VBlank. So the VBlank is actually doing other jobs other than just the music. We have used it before in the Mintile example. That's the graphics example that you could see running in the background. That also uses the NMI interrupt handler, and that is something that was quite important when it came to actually using this example. Now, here is the NMI handler here. You can see we've got the start here. We are pushing all of the 3 registers, the accumulator X and Y, onto the stack here, and we're popping them off the stack at the end before our RTI. The NMI interrupt actually backs up the flags. It pushes them onto the stack automatically, and the RTI command automatically pops them off the stack. So we don't need to do the flags register, but the other registers we need to push and pop off the stack. Now, at the start here, we are effectively starting a DMA transfer of the buffer for the tile map, and we are sending that. And then after that, we are using the ChibiTracks program, which is my music tracker, my music player. And this uses some entries in the 0 page. Now, they're named in pairs, H, L, D, E, B, C, and IX, so that's 4 pairs. The names match the Z80 registers because this was ported from the Z80, so that's just backing up and restoring the entries in the 0 page that is used by ChibiTracks and also other parts of my code. Now, one thing that is important to bear in mind is that while we can update our music at any time, we just want to update it once per VBlank to keep the speed correct. We do actually need to make sure that our video is updated during that VBlank while the screen is not being drawn. So I'm doing the DMA transfer first, and then I'm updating the sound second. Now, actually on the Super Nintendo, I believe it's generally so fast that that's not going to be a problem anyway. That was a big problem on the NES though, because the NES is much slower, of course. But as I say, it's just making sure we do things in the most appropriate order. So that's how I'm doing things here. Now, how does the ChibiTracks software work? Well, it's very straightforward. We basically have a couple of parts that we need to load in memory, the source code. ChibiTracks is the multi-platform player, so that is common to all 6502 systems. There's some shared modules here for ChibiTracks Tweener and Fraction 16 that I used for the calculation of the in-between notes. So I was planning on reusing that code, so I've split them out into separate modules. We also have Chibi Sound Pro. Now, that is the platform-specific driver, so that actually sets up the SPC 700 processor, the sound processor of the Super Nintendo, which is a right pain, but that's all being done by this part here. And then all we need to do is we need to provide a music file. So we've got song 1 here, and we're loading this binary song into memory there. Now, beyond that, ChibiTracks needs about 128 bytes of memory that is used for various purposes. This is basically, it's keeping a cache of all the sound register settings of the SPC 700 on the 6502 side. It also keeps track of the various settings of the song, and you can see we're defining the song variables just shortly after the actual main data there. So that's all of the data that the Chibi Sound driver and also the ChibiTracks music player require. We've got some options here that we can enable or disable. Allow relocation allows the binary music file to be loaded into a different destination address to the one that it was assembled with by the Chibi Tracker software that I wrote for Windows. So that exports the file. You specify the intended load address during that export, and it's coded in various places within the offset of that file. However, loading into different addresses is very convenient, so you can enable that option here. It just makes the player a little bit bigger and very slightly slower. Another option is allow speed change. Now, this alters the amount of delay after each line of the patterns of the music file. Now, if we enable this, it does slow down the player quite a more significant amount than allow relocation. Not much, but a little bit more, and it makes the player a little bit bigger. However, it gives us a benefit that we may want to take advantage of. Now, this song was actually written for a 50 Hertz system. But this is a 60 Hertz system, so the song is actually playing a little bit fast if we don't change the speed. So if I play it here, that is the song playing at the default speed, but I can override the default speed and change it from 5 to 6. And it just changes, it's just slightly slower, and that is the correct speed for this song, give or take. So by enabling that allow speed change option, we can actually do that. If I disabled this, we wouldn't be able to change the speed, and in this case, if I play it now, you'll find it plays far too fast. Well, that's not good at all. Why has that happened? Well, this song, it requires the speed to be changeable at playtime. The Chibi Tracker software can actually export, and it can actually pre-multiply the speed, and that will basically mean that you can't change the speed at playtime, but you don't need to enable this option here. So it depends how you export the binary file. This one was exported without the pre-multiplied speed, so we do need to allow speed change for that to work. Now, actually starting the song is very straightforward. All we need to do, we run Chibi Sound Pro init. On this system, that will actually initialize the SPC 700. It will transfer the program to the SPC 700. The program on the sound processor side actually just receives register settings. The actual job of reading in the music file, deciding when to change notes and things, is all done from the 6502 side. That's not the most efficient way of doing things from a processor point of view, but it is the only realistic way of doing things in my multi-platform tutorials, because otherwise I would have to rewrite the entire music player on the SPC 700, and I am not familiar enough with that processor for that to make sense for me, because I'm writing tutorials for a whole wide range of other systems that, to be honest, are far far more interesting to me than the Super Nintendo. So this is a trade-off solution that allows the music to play, and it allows me to get the job done as quickly as possible. So we do that initialization. We then load the address of our song here. It's song 1. So we're loading that into song base, a 16-bit value there. We then run ChibiTracks start song, which reads in all of the settings from song base, and it then initializes the player. And then all we need to do is turn our interrupts on, and that will actually start the music. Everything else is being done by this play routine here. Every time we run this, it updates the sound, it sends the new settings to the sound registers, and that will update the actual playing hardware. So that's how we do it. So there we go. As I always say, you can go to my website and download the source code and the build scripts for today's example, and you're welcome to use any of it in anything you can. And if somehow you manage to use it commercially, good luck to you. I really don't care. Make the best of it you can. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.